In this video, we're going to look at a problem called the resource allocation problem. And you can see from the verbiage that the company manufactures two products, X and Y, and each of these products uses two resources, A and B, during the manufacture. You've got the detailed information. Each unit of product X requires 12 units of resource A and 14 units of resource B, and each unit of product Y requires 10 units of resource A and 2 units of resource B. We have resource availability, so during the current planning period there are 200 units of A available and 150 units of B available. Further, each unit of product X yields profit of $200 for the company, and each unit of product Y yields $80 profit for the company. And finally, the company is contractually bound to produce at least 5 units of product Y for a supplier that, through a previous arrangement. And so the resource allocation question is, how many units of X and Y should be manufactured during the current planning period? So as before, what we want to do is look at our decision problem and say, what decision is being made here? What are we trying to decide? In this case, we're trying to decide the number of units of X and Y that should be manufactured. And then the second problem is, or the second question we have to answer is, how do we make the decision? So what is the metric to use? And what we're going to use is profit. In particular, we want to maximize the profit made to the company by producing these units of X and Y. So before we start to formulate the problem, I'm going to collect the information in a slightly different form. So what I've done in this table is I've extracted the information from the verbal description of the problem and provided only the pertinent information in our table. So we can see we have our individual part types X and Y for each row, and associated with each row I have the profit for that part type, the resources consumed, and the minimum number required. Associated with my resource columns, I also have the amount available for each resource. And so we haven't really done anything here other than consolidate the information and provide and present it in a form that's more amenable to formulation. So again, our objective, our metric for selecting the number of parts of X and Y is we want to maximize profit. And we say that our profit is a function of the number of X and Y that we produce. So for each X, we get $200, and for each Y, we get $80. So our decision variables X and Y, and our decision variables are X and Y, and our objective function is then simply to maximize the sum of the profit for each unit times the number of units. So if this were all there was to it, we would simply make an infinite number of X and an infinite number of Y, and we would have infinite profit. Clearly we can't do that. We're bound by our resource constraints. In particular, we're bound by constraints on A, so that we can't produce more products than the resource A will support. So in order to formulate that constraint, we need to express the constraint in the context of our decision variables. So our constraint, subject to our resource constraints, and our resource constraint says 12 times X plus 10 times Y must be less than or equal to 200, and 14 times X plus 2 times Y must be less than or equal to 150. And so this is going to limit these two constraints. We're going to limit the amount we can produce by our constraints. And finally, we have our constraint on our minimum. So the minimum value, minimum number of Y, has to be greater, or the number of Y has to be greater than or equal to 5. And so finally, we also by default, X has to be greater than or equal to 0. It doesn't make sense otherwise. So clearly we have just formulated the problem as a linear program. Our objective function and all of our constraints are linear, and the decision variables are non-zero or greater than or equal to 0. And so we can solve this problem using a variety of methods to solve linear programs. We might also introduce integrality constraints on our two decision variables, x and y, depending on whether or not we want to force the solution to only include integer values. So now that we have our optimization, our LP formulated, I'm going to jump over to Excel and develop an Excel model that uses the Excel solver to solve this problem. And so you can see what I've done is I've just transcribed my information. So I have basically the information in this table just transcribed over into Excel to give us a starting point. So the first thing I'm going to do is I'm going to just define my decision variables. Define my decision variables here. And my two decision variables are the number of x and the number of y. And so by convention, I usually make the background of my decision variables as x. Is yellow, and I'll just put two values in to sort of make sure that we have everything correct. Then over here on my profit column, I'm going to compute the profit based on the decision variables. So I compute my profit is 200 times the number of x plus 80 times the number of y. And so now we have 360 as we would expect. And then again, by convention, I'll just make this light green, signifying that it is the objective function value. We can also, now that we have our decision variables, we can compute our constraint, our resource usage. So I'll just say we have 12 units of A times the number of X plus 10 units of Y, of A times the number of Y, sorry about that. And so we've used 32. And the similar calculation for B, 14 units of B times the number of X plus 2 units of B times the number of Y. And so now for each case, we have computed our resource usage. And so I can go in my model and I can say, well, what if we did 3 and 4, for example? And we can see that our profit goes to 920 and we're still under our resource constraints. So before we do the solver, let me fix my spelling error here. D-E-C-I-S-I-O-N. Saw that in the review. There we go. Decision. So what I want to do, these are my decision variables, and what I'd like to do is now set up the optimization. So if we go back to our formulation, we can see that we maximize our profit. We have two resource constraints, and then we have two minimum value constraints, one for y greater than or equal to 5 and one for x greater than or equal to 0. And so we can put those in our formulation. Just go to Data, Solver, bring up the Solver parameter page. And first thing I want to do is specify my objective, which there it is, 920 in cell B5. And then how is Excel going to determine the options? So it's going to change cells F3 and F4. Those are our two decision variable cells. And so those are our basic objective value and our decision variables. And now we need to define our constraints. So our first set of constraints basically says I want the value of resource A to be less than or equal to my constraint of 200. Then we'll do the same thing for B and say I want my computed value to be less than or equal to the value 150, and so that's there. And finally, my minimization, I want my computed value here, or my selected value, to be greater than or equal to the minimum. And we'll do the same thing for X and say the value selected value is greater than or equal to the minimum. And so if we look at our constraint set, here we go. We have our two resource constraints and we have our two minimum constraints. And now let's just give it a go and see what we get. And so when we execute the solver, it says, well, the minimum that I can do, or the maximum I can do, is 2,586.207, and note that my two decision variables have non-integer values because we didn't specify integrality constraints. So you can see that we have the absolute maximum, guaranteed maximum, because it is a simple LP to solve. If we want to add integrality constraints, we can simply go back in to our formulation, add a constraint, and do our cell reference, select both of our decision variables, and say I want both of these to be integer. And so now we have our integrality constraints, and if I resolve, we can see we have a different solution, x a value of 9, y a value of 9, and you can see, as we expect, we didn't meet our constraints exactly, so these are no longer binding constraints because of our integrality constraints we're unable to add one more unit of either one. And so you can see using a very simple Excel solver and using our LP formulation, we can solve this general resource allocation problem quite easily. The key when we developed this formulation was in identifying from the verbal description, from the qualitative description of the problem, extract the things that we want. So extract our decision variables, in this case x and y, identify how we're going to select values, in other words, maximizing profit in this case, and then identify what constrains our solution. And in our case, what constrains our solution are the resource requirements for A and B, and the minimum number of units to produce for Y.